Hi and welcome back. We're discussing the general idea behind stationary methods. Now, stationary method is also called a matrix split method, and this will become very clear when we look at how it's set up. So we're solving a system of equations, ax equal to b, and A is an n by n matrix, and of course we'll assume that A is non-singular because we'll have a unique solution x that we're aiming to compute. Now, the main idea behind these stationary methods is to simply split the matrix A into two parts. And here I've called them M and N, and I write A as M minus N. And we'll see later why we write it as M minus N, which may sound a little bit funny. Why don't we write M plus N? But it's just because then later on we don't have to write that minus sign. Now, the idea is very clever. We take AX equal to B, we implement the splitting, m minus nx is equal to b, and then we simply move the minus nx part to the other side of the equations. And we get mx is nx plus b. Now, when you stare at this splitting for a little while, you could maybe imagine finding an iterative process where we take the x on the right-hand side and make that the old iterate, the old approximation, and on the left-hand side, we put the new one that we're after. So we would get an iteration process like this. We have an approximation xk at some step in our iteration process. We plug that in the right-hand side. This whole right-hand side now is known, nxk plus b. And we solve for xk plus 1 by solving this system. We start with an initial guess x0. So we take that x0, we plug that in here. So k, the iteration counter, is 0 at this point. We know this, we compute x1. Then we upgrade k becomes now 1. We put in x1 on this side, which is now known. We know this right-hand side again, solve for x2. Plug in x2, solve for x3, and so on. Now, hopefully in this process, we've chosen m and n so well that this will converge, and it will converge to the correct solution. Now, of course, when we're looking at this equation, we can immediately see that m must be non-singular. Otherwise, this system, equation 1, will not have a unique solution. So that's our first requirement. M is non-singular. Now, of course, this equation 1 must be cheap to solve, because if it were expensive, then what's the point in the iteration? Then we're going through an iteration process where we solve a lot of these systems but every time it's expensive, and maybe then the total cost would be higher than solving ax equal to b directly. Now, looking at 1 and looking at the system that we need to solve, you may think, oh, the cheapest and the easiest m that we could possibly take is the identity, right? If m is the identity, then I just get the equation xk plus 1 is equal to nxk plus b, and I don't even have to solve for the system. I explicitly get xk plus 1 as a function of xk. Would this work? Let's have a look. So I've chosen this matrix A, just a 2 by 2 matrix with that b, and that gives us the solution x is 3, 1. And so we're trying to use this iteration with m equal to the identity to find a good approximation to this x. So here m is equal to the identity, n then of course is the identity minus a, because m minus n is equal to a. And that will be this little matrix, minus 1, minus 1, minus 1, minus 1. And we need to find an initial guess, x0. We need to choose it. And very often we choose something simple, like maybe x0 is equal to b. In this case, I just chose x0 is equal to 1, 0. So the iteration itself will look like this. Okay? xk plus 1 is explicitly given as this little matrix times xk plus b, which is 7 over 5. Now, when we start plugging in x0, we can find x1 immediately to be 6, 4, x2 to be minus 3, minus 5. So it looks like we're getting a little bit closer, but then we plug in x2 to find x3, and we see that we get 15, 13. That's a little disconcerting. And then x4 actually gives us minus 21, minus 23. And clearly, this process is not converging anywhere near the real solution x, which was 3, 1. Not good. Now you can argue, say, well, you choose a particular initial guess. Maybe this iteration process will depend on it. But really, do we want an iteration process success to depend on our initial guess? Now, we really want these things to work at all times. So clearly, choosing just any m, in this case an m that gives us a very cheap iteration step, is not necessarily going to work. We need more conditions. Really, when we're looking at this iteration process, there are these questions that we'd like to ask ourselves. And we're going to be answering them in the remaining core videos. The first one, of course, is that if we actually converge in this iteration process, will we converge to the correct solution? It would not be a very useful process if we did converge, but the answer that we got was nowhere near the actual solution X. So that's the first thing we'll have to check. Then the next question, of course, is can we find some general criteria for M and N so that we know that we will always converge independent of the initial guess X0? And then, of course, the next one is, if we converge, how fast will we converge? And really, how do we control that as well? And the next question, of course, is that if we converge, how fast will we converge? Now, that will depend naturally on the choices of M and N, but can we find some general guidelines to help us choose M and N so that the convergence is fastest? Now, the other question is, how do we control this iteration process? Until now, we've just been saying we want a sequence of approximations, x1, x2, x3, and so on, until we get close enough to the actual solution X. Now, the problem is we don't know X, so how can we measure that we're close enough? And then the last thing, of course, is, are there very well-known splitting methods that we may be able to apply directly to our problem, or do we have to reinvent splitting methods every time we have a new application? So I look forward to seeing you in the next videos.